let me begin by saying what a random orthogonal matrix is. So the technical definition is it's an orthogonal matrix that's distributed according to the Haar measure over the group of orthogonal matrices. So this is quite a technical definition because it involves this thing called the Haar measure, but we don't really need to know the technical details for this talk. All that really matters is just that this is the natural way of drawing a random orthogonal matrix in a uniform way from the complete set of orthogonal matrices. And the only property I'll need is this second bullet point, that if you have two such matrices and you multiply them together, or you multiply them into another orthogonal matrix, then you still have a Haar distributed matrix. So this Haar distribution is invariant under multiplication on the left and the right by orthogonal matrices. So that's what I mean by a random orthogonal matrix. So what do I not mean by a random orthogonal matrix? Well, I don't mean a random householder matrix. So if you take a random vector and construct a householder matrix, that's not actually Haar distributed. Likewise, if you take a random skew symmetric Si minus S inverse, that's orthogonal, but it won't be Haar distributed. And the same thing goes for the exponential of a random skew symmetric. That also won't be Haar distributed. So what's the connection here with so the idea here is that we want to form a test matrix that we're going to test one of our algorithms with, but we want to have a matrix that's random, but where we know its singular values. So the idea is to choose some singular values, sigma 1 to sigma n, put them in this diagonal matrix sigma, and then we pre and post multiply by random orthogonal matrices. So this idea goes back to the 1980s. I first saw it in the context of LAPAC, where Demel and McKenney programmed this within the LAPAC test matrix generation suite. And this code, I think, has made its way into subsequent packages like ScalarPack and so on. I programmed this myself in MATLAB in one of my toolboxes, and that's now in MATLAB proper in Gallery. So Gallery RandSVD built into MATLAB will form the matrix in this way. And I also put this into a recent package I did with one of my PhD students for Julia. So this is a nice form of test matrix because you get to choose the distribution of singular values while keeping the matrix random. How do we implement it though? How do we actually compute a P and a Q that are from this this Haar distribution? Well, there's a method that's been known for many years, method 1. I think this goes back to the statistics literature. So what you do is you take a random matrix of normally distributed numbers, so normal, mean 0, variance 1. That's rand-n in MATLAB. You compute a QI decomposition, and then you just modify you take the Q and you have this correction to the signs. So, but basically, it's the Q from the QR factorization of a random normal matrix. And it's been proved that that will generate a Haar distributed matrix. But clearly, there's a bit of waste here because we're computing the matrix R, and then we're only using it in terms of the signs of its diagonal. So this is rather inefficient. And in 1980, Pete Stewart found a better way of doing this. So what he was able to show was you don't need to form R at all. What you can do is construct this product of householder matrices. Each householder is based on a random vector, normally distributed. So you form the householder that reduces X to the multiple of E1, and you then have in product form this matrix, and these vectors, I should say, are gradually decreasing in size as you go along. And you now have in product form a Haar distributed matrix. So this is good, of course, because if you now want to apply Q to another matrix or vector, as we do when forming P sigma Q transpose, you don't need to form Q explicitly. You can use this product form to construct the product. So this is available in MATLAB through Gallery QMult, and it basically halves the cost measured in flops of forming a RandSVD matrix. So for an m by n matrix, the flop cost is about it should be m cubed plus n cubed, not m squared. So it's cubic in the dimensions to form a RandSVD matrix. The problem is, of course, if we're thinking about extreme scale computing, doing something that requires m cubed or n cubed flops is going to be rather expensive. So the question is, can we do better? Can we get the matrix has got mn entries, so I will have to do at least mn flops, but if I can do it within order mn, then I'll be happy. So going back to the original formulation, P sigma Q transpose, I will have to give something up in order to get a faster computation. And what I'll give up is the fact that P and or Q are hard distributed. Now, in all the literature I've seen, nobody's ever really said that we actually need P and Q to be strictly hard distributed orthogonal matrices. I'm not aware of any reason why you would require that. So we can consider giving up that property. So one thing you could do, which is natural from Pete Stewart's construction, is rather than take this the full product of householders here, you could just take, say, K of them for both P and Q. And that would clearly reduce the cost. And in fact, I have worked on this a few years ago, but didn't write anything up. What I would say about that is you'll need to take K fairly small in order to get a significant savings in cost. But if you take K too small, you'll end up with a matrix that's a low rank perturbation of a diagonal matrix. And that probably isn't a good idea to have that sort of low rank structure lurking behind A. So what I'm going to briefly describe is how to form such a matrix in order mn flops. And the idea is we're going to simplify our orthogonal matrices here. So on the left, I've put a Q that for now will be any matrix with orthonormal columns. So A is rectangular, therefore Q and W will be rectangular here in order to get a compact representation. Now W, though, I will take as a random, essentially a random householder matrix, although it's a rectangular generalization of a householder matrix. Okay, so I've got a general orthogonal Q, which I'll explain how I choose that shortly, and then the W is going to be a rectangular generalization of householder with a random vector. If you have a square matrix, and if you only care about the condition number, so the condition number, of course, is sigma 1 divided by sigma n, then it turns out that if you set all the intermediate sigma values to 1, you get some savings in the construction. So basically some flops just disappear. And so that gets a slightly faster computation. So in this work that I've done with Max Fassi, who's a postdoc in Manchester, we've used this idea to construct a rand SVD type matrix. It's order mn flops plus the cost of Q. And the important thing is that we've been very careful to make sure that as little communication as possible is required. I've been talking about flops so far, but communication is probably even more important. And so we've done things in such a way that communication is kept very low. So how are we going to choose that matrix Q? So we could keep it hard distributed, but that would be quite expensive. So what we actually do in practice is take, in fact, we would say take any matrix for where you have an explicit formula for the entries. Here's the one I'm going to take in the experiment. So Qij is given by this expression. So this Q is actually symmetric and orthogonal, but the point is you can compute Q without any communication at all. You just compute the formula for each ij and you're done. So that's a very fast to compute that Q, and it's a full orthogonal matrix. So I'm just give you one experiment. So I'm not going to go into any details at all here. But what this experiment is about, this is all done in C. And we've got nodes that are 16-core Intel Xeons. And this is a 20,000 by 20,000 matrix I'm forming. And I just want to show two things. So on the left-hand side, and on the x-axis, we've got the number of MPI processes. And I'm comparing PRSVD, which is a C translation of the LAPAC rand SVD generation code, against, we've got 4 different variants of our algorithm. So the main thing to note on the left is that this is the time for the LAPAC, full rand SVD approach with true random orthogonal, and we're getting clearly a significant speed up by using this this technique where we relax the requirement that we have exactly random orthogonal P and Q. On the right-hand side, I'm showing the speedups, so the time for one processor over the time for P processes, and you can see that there's a little bit of variation amongst the algorithms, but one of them, this one at the bottom in the turquoise, is getting very close to perfect speedups there. So that's just a feeling, just to give a quick feeling for the benefits that this approach gives you in terms of using this for very large dimensions. The only reason we've restricted to 20,000 here was that this one is so slow. So we have other tests with much larger matrices that give similar performance. So now we can construct such a matrix. What are we going to do with it? Well, we're going to use it to test some algorithm. And I know that in the cows group, you've been using this sort of idea to test the QWH SVD approach, where this is very natural to compute an SVD, to form the SVD you want and try and recompute it. But another thing you might do is use this as a test for solving linear equations. So AX equals B, n by n system. This could be a test matrix for that. So one of the things that we have to worry about when we solve x equals b by a direct method like LU factorization is the growth factor, which I'll recall here. So you take the biggest element that you ever see during the elimination and you divide it by the biggest element you started with. So this is at least 1 clearly. And Wilkinson, in his famous 1961 paper, showed that the Gauss elimination produces a backward error where the norm of the backward error matrix is bounded in terms of this growth factor times the unit round off times the norm of A, and then there's another polynomial term here. But basically the growth factor, if it's large, is suggesting we will get a pretty poor solution to our linear system. And so this then focused attention on how big the growth factor is, of course, and this has been something that's been worked on and looked at for many years. So I'm going to just say a bit about what's known, and then I'll show you an experiment. So following on from Wilkinson's original work, in fact, without pivoting, as he pointed out, the growth factor can be arbitrarily large, and that's why we pivot. We have to pivot to get numerical instability. With partial pivoting, he found this example here. This is the 4x4 case, where you get 2 to the n minus 1 growth, and that is actually the very worst case you can have. There were a couple of papers where Steve Wright and Leslie Foster found examples arising in practice where you get large growth with partial pivoting, but they are rather special cases, and this is not something that's likely to happen to you in practice. And my brother Des and I found some matrices where you get growth at least n over 2. I'll say more about that in a moment. But the general consensus is, based on what almost 70 years of digital computing, the growth factor for partial pivoting is almost always small in practice. And we don't really know why that is. So it's a big open problem to come up with a good explanation of why the growth factor is normally small for partial pivoting. So I'm going to show you a quick experiment, and I'm going to use this MATLAB function here. So the function takes in a matrix A, a square matrix, it computes the LU factorization, it throws away the L factor, and then it computes an approximation to the growth factor. The reason I say approximation is I'm only looking at the final U, so I'm not looking at all the intermediate numbers here. This is just to make this doable via LU. I also have a function in my toolbox that can compute the actual growth factor. So, but this is good enough for our purposes, this lower bound that we get from the GF function. So what I'm going to do, I'm going to take some random matrices, 10 by 10 random normal matrix, compute its growth factor, 1.5. 100 by 100, random normal, growth factor 4.5. 1,000 by 1,000, now up to 16. 10,000 by 10,000, about 50. So this is exactly what you'll find if you go into MATLAB and do this with some other random matrices. Typical sorts of numbers. But now let me do it with a random SVD matrix. So 1,000 by 1,000, condition number 10 to the 8. The condition number doesn't really matter here. Now in the MATLAB random SVDs, there's 3 different modes, or 4 different modes, that which determine the single value distribution. I've taken mode 2, and I get growth 75 for 1,000 by 1,000 matrix. So this is extremely unusual. Going back to the random normal, 1,000 by 1,000 gave me growth of 16. 10,000 by 10,000 gave me growth of 50, but I've now got 75 from 1,000 by 1,000 matrix. So there's something strange going on here with this random SVD mode 2. It seems to be giving extremely rare large growth. And so is that a concern? Well, what's the largest n that we're solving today on dense x equals b problems? I think it's about 10 to the 7. So if you're solving a problem in single precision of that size, and you get a growth factor of, say, 10 to the 7, growth factor of n, then you are potentially losing essentially all precision in the solution, because the growth factor times unit round off will then be of order 1. Secondly, nowadays we're often working in lower precisions like IEEE half precision, and there, of course, the unit round off is about 10 to the minus 3, 10 to the minus 4, but even more so, this IEEE half precision has a very narrow range. The largest number is about 65,000. So if you have any 7 times 10 to the 4 and you have linear growth, you'll get overflow in half precision. In fact, this is how we spotted this issue with the mode 2. There was overflow in an LU factorization, and we just couldn't understand how this could be. It just didn't seem right. The code was correct. We didn't expect this, but it turned out we were getting large growth. So what I'll explain in the rest of the talk is where this large growth comes from, and I'll explain just how bad it is. And this is joint work with Des and Sri Pranesh. Sri's a postdoc in Manchester. So just let me show you, first of all, an experiment to give a feel of what's going on here. So these are some RAND-SVD matrices. The singular values in mode 2, they're all equal to 1, except for the last one, which is sigma n, and that's the one that we vary, and that will determine the condition number of A. So here I've got n on the x-axis. For each n, I've generated 10 random matrices of this type, and I'm showing you the mean growth factor, first of all, for partial pivoting in the blue curve. There's something called Rook pivoting in red. Don't worry if you don't know what that is. By Wilkinson, there's a much stronger pivoting strategy that has a much better growth factor bound than partial. And what we see is that these growth factors are growing at a fair old rate here. At the bottom, we've got the growth for RAND-N and RAND. So this is the green circles are random normal. The purple crosses are uniform random 0, 1. So this is the typical sort of growth you would see if you generated a random matrix in say, MATLAB. This is what we're getting with RAND-SVD, much larger growth and much faster rate of growth as well. What's the black line? The black line is a lower bound I'll derive in a moment. So I can prove that the growth should be for large n above that black line, as indeed it is here. So let's see if we can explain what's going on. First of all, just a reminder of a result from many years ago with Des, where we got a lower bound on the growth factor. So this works for any matrix A, any non-singular A. If you look at the largest element in A, alpha, and the largest element in A inverse, call that beta, then you form the product and reciprocate to get theta. Then it turns out that theta is at least n, and then you can show that the growth factor will be at least theta for any, essentially for any growth factor, for any pivoting strategy rather. So the growth will be at least theta. However, if you just take a sort of random matrix, you'll find that theta comes out much less than 1, and this result doesn't tell you anything. So in order for this result to be interesting, you have to have a matrix with fairly small, with fairly large theta. And in that paper, we identified certain specific orthogonal matrices that had that property. Well, here we worried about these random orthogonal matrices. And so what I want to do, first of all, if in my RAND-SVD matrix, I take sigma n equals 1, then I get, so the sigma term is just the identity. So my RAND-SVD is now A is PQ transpose with both P and Q random orthogonal par distributed. And remember earlier I said that the product of such matrices is again from the same distribution. So now A is just itself a random orthogonal matrix. And there's a result in a paper by Zhang that shows that the probability that this largest element of such a matrix is bigger than this number here goes to 0 as n goes to infinity for any epsilon. So what that means is that essentially what he's saying is that for large dimensions, the size of the elements in a random orthogonal matrix are not too big. And in fact, this means I can take alpha is beta is 2 root log n over n in the result on the previous slide, and then applying that result, I get this lower bound for the growth factor for a random orthogonal matrix from the Haar distribution. So the growth should be for large n, at least n over 4 log n. And of course, n grows faster than log n, so this is something that's increasing fairly rapidly. And again, this is for any pivoting strategy. Let's just see how that compares with what we see in practice. So now generating a single random orthogonal matrix. As before, for each n, I'm taking 10 matrices. This time I'm showing you the maximum growth factor for partial, root, and complete pivoting. So the black line is the n over 4 log n that we saw as a lower bound on the previous slide. And we can see that the growth here is much larger than the lower bound we have. So getting up to over 400 for a matrix of size 2,500. So that was for just a single random orthogonal matrix, but what about for a rand SVD matrix? That was where we originally saw this phenomenon. So how can we analyze that? Well, for mode 2, since most of the singular values are equal to 1, I can write my mode 2 random SVD in the following way. I can write it as the PQ transpose plus a rank 1 perturbation. And the rank 1 perturbation involves the last columns of the P and the Q, and then the sigma n, that's the one parameter I have, that's the smallest singular value. All the other singular values are equal to 1. So I've got random orthogonal plus rank 1, and I've just shown that that matrix, the PQ transpose, will generate large growth. So can I then prove something about the growth for A? Well, I spent quite a lot of time looking at properties of hard distributed matrices, thinking that they would be very important here. It turns out, though, that they're not that important because the result I need is a bit more general. So if W is any orthogonal matrix that has large growth, and you make a rank 1 perturbation, it turns out you tend to preserve the large growth as long as that rank 1 perturbation is not too big. So the norm is less than 1, let's say. So this property that I need is not particular to that matrix being hard distributed, particularly. So how can we proceed? Well, as soon as you see a rank 1 perturbation, you naturally think of the Sherman-Morrison formula. That's something we use a lot in solving linear equations. For example, if you have a rank 1 perturbation, you think about using that formula. So that's one approach you can take. And in the paper, we give some analysis based on Sherman-Morrison. But I'd like to show you just very briefly another approach that gives a slightly better result and is a bit more direct. And this harks back to some old determinantal formulae that are probably not so well known, but have been around for many years. So here's the setup. You give me a W that's orthogonal and has large growth. I'm going to have a rank 1 perturbation of norm at most 1. And I'd like to see whether whether A will have large growth. And the key observation is that there's a formula for the elements of the LU factors in terms of determinants. So here's the formula for Uij. This is the U factor of W. Okay, so you have to take a couple of submatrices of W. It's the ratio of those determinants that gives you Uij. I think I first saw this in Gantmacher's book from the 1950s on matrix analysis. So I would like to get the formula for the corresponding element of the U factor of A, but since A is just a rank 1 perturbation of W, and since you can easily manipulate determinants of rank 1 perturbations, I can, without too much difficulty, get this formula at the bottom. So the new Ij element over the old one is equal to this ratio. So I'm going to assume that this number on the denominator is big, because if I've got large growth, I'll just look at the Uij that gives large growth. And that will tend to be in the bottom right-hand corner of the matrix. So what I need to do is to show that this ratio is of order 1, so I can conclude that U tilde is also big. And if you look at this ratio here, the problem is I've got two inverses of submatrices. So if, for example, that this submatrix I'm inverting here is very ill-conditioned, that will make the denominator big, and then I'll have the whole ratio small, and that won't be what I want. Likewise on the top. So I'd like to somehow show that these submatrices of an orthogonal matrix are going to be fairly well conditioned. So the natural thing to do is to look in the literature. What do we know about the condition numbers of submatrices of orthogonal matrices? Well, if you try this yourself, if you Google this or you look in Horn and Johnson or any of the standard texts, you'll find many references on submatrices of symmetric matrices. For example, there's all kinds of inequalities for the eigenvalues of submatrices compared with the whole matrix. But there's very little that you can find on submatrices of orthogonal matrices. And I was quite surprised how little I could find. Eventually, though, I realized what I needed, and I will just explain that by stating this lemma. So this is what I need for the analysis. I'll explain where this comes from in just a moment. But what this says is that you take an orthogonal matrix, you break it into 4 pieces, and I'm going to assume that the bottom right-hand corner piece is small. So the k by k bottom right-hand corner, k is less than n over 2. Okay, so W22 is small compared with W11. And the lemma says that most of the singular values of W11 are equal to 1. And there's just k of them that are not equal to 1. And they are bounded above by 1. So is that obvious? That given that W is orthogonal, that most of the singular values of that leading 1, 1 block are equal to 1. It's not obvious to me at all. However, the proof is actually very easy if you use something called the CS decomposition. Now, some of you may have heard of this. If you look in Gulliver van Loon's book, it's described pretty early on in the book. What the CS decomposition is the SVD specialized to a block, to an orthogonal matrix when expressed in block form. So it's a special version of the SVD that applies to orthogonal matrices. So I feel it's sort of known, but not that well known. And in fact, I'd forgotten about it when I was doing this work and had to sort of rediscover it and realize that this was the tool I needed. So what I'm going to do is, essentially, I can use that tool to argue that they don't cause any problem when I invert. And the remaining single values, I can then give some argument that under suitable conditions, they are also not too big, or not too small, rather. And hence, I can argue as to why the growth is going to be big. Okay, so that's my argument as to why we saw the growth we saw in this slide here. That the growth that happens for a single random orthogonal, it also happens for a rank 1 perturbation, which is what we've got in this mode 2 random SVD matrix. So my final comment is about iterative refinement. So I've done quite a bit of work in the last year or two on solving X equals B, exploiting multiple precisions. And the basic idea I've just summarized in a very broad way here. So we have 3 precisions, let's say. The medium precision I'll think of as the working precision. You can think of that as W, as a double. I've got a low precision arithmetic as well. Think of that as perhaps half precision. And then I've got a high precision, which could either be quadruple or it could just be the same as medium. So the idea here is I'm going to factorize A in low precision, trying to exploit some fast low precision arithmetic I might have on my, say, NVIDIA GPUs. I'm going to then use those LU factors to solve the linear system. But of course, the solution I get will be fairly low accuracy, maybe 4 digits correct at best. So now I want to refine the solution. So following the standard refinement idea, I'll compute the residual in high precision. I'll then solve an equation for an update, D, using the LU factors I computed in low precision, and then I'll add that to X to hopefully improve X, and then I'll go round again and repeat this process as many times as necessary. So that the old style refinement would be to just solve AD equals R. The newer idea is to use the LU factors that we computed at the top to precondition the equation and then solve by GMRes. Okay, so I call this GMRes based iterative refinement. And this is what's used, for example, in the HPL AI benchmark. So the question that now arises is, we've just seen that RandSVD mode 2 gives rise to large growth in the LU factors. So it gives you not very good LU factors, in addition to the fact we're already in low precision here. So the question is, does that damage iterative refinement? Does that destroy the convergence of refinement, the fact that we now have much less good LU factors? And since we're using them as preconditioners here, for example, are they now such poor preconditioners that this whole thing just fails now? Well, we tried this out, and in fact, the good news is it doesn't cause any problems. Iterative refinement is able to cope with the lower quality LU factors caused by the large growth. And in a way, that shouldn't be too surprising, because back in the 1970s and 80s, there was a whole strand of work where people were starting to use iterative refinement as a way of, not just as in the past, improving the accuracy of an already quite accurate solution, but they were using it to cure instability. So the idea was that you might maybe solve X equals B without any pivoting at all, and then hope to see whether whether the refinement process could cure the instability. And there were a number of papers by Bob Skeel and other people who showed that yes, refinement could actually cure the instability as long as it wasn't too bad. And so what we're seeing here is that the same is true with the GMRes approach, where we're using the UNL as preconditioners. So just to wrap up then, we've identified a new class of random and dense matrices where you get relatively large element growth in LU factorization. And it's precisely the RAND-SVD mode 2 matrices. And you can choose the condition number arbitrarily. It doesn't matter what you take for the condition number, you still have this lower bound here. So this is a bit surprising because these matrices have been in MATLAB ever since the beginning, and yet nobody had noticed, including me. I often use Gallery RAND-SVD to compute test matrices. For some reason, I must have never tried mode 2 on an LU problem, but they have been lurking there in the background all this time. And what I explained at the start was we can form approximate RAND-SVD matrices by relaxing the requirement that the P and Q factors are exactly hard distributed, and to get a much faster construction with little communication and much better performance. But I would just say beware mode 2, because you will still get large growth with these for mode 2. And if you'd like to get hold of the slides, there is a link there, bit.ly rom-hpc. Thank you, so I'll stop there.
Great. Thank you so much. Thanks for the great presentation. All right, let's see if we have a question from the audience. I have a couple, but let's see first if some of the audience wants to be the first one.
Well, I'll just add my thanks to Nick for showing up to our HICMA group meeting. Since, I mean, normally we have, as Hatem says, a masked guest, but since we actually knew who you were going to be, I told people you're going to meet the most practical of all theoretical numerical analysts. and both sides of that are intended to be a compliment, and you lived up to it in the sense that you know, HPL and HPLAI now depend on a very systematic but not so expensive way of generating these tests. I had no idea, you know, how relevant this sort of obscure topic was going to be. And then, of course, you know, knowing that your signature in recent years is exploiting low precision, it all ties together, you know, very nicely. This is a really nice and surprisingly, you know, fresh presentation. Especially, I wasn't aware of a lot of things in here. One question is about this hard distribution. You mentioned that, you know, it's overly strict compared to what is normally needed. I guess all it means is that if you have a distribution of such matrices and you multiply them by an orthogonal matrix, it stays the same. But where did that come from? Who invented this strict criterion, and what is the motivation behind that in terms of, you know, the history of this topic?
Well, the history in terms of the RAND-SVD test matrix is, I think, as far as I know, goes back to Jim Demmel and Alan McKenney. They decided to use that, and I guess they would have known about Pete Stewart's paper. And in fact, it probably actually goes back to Limpac before that, in the sense that I think the reason Pete Stewart wrote that paper, he wanted to construct test matrices for Limpac. And although I don't think Limpac had maybe a formal test suite in the way LAPAC does, I suspect they probably used them there. And yeah, it was natural. And of course, in those days, I guess maybe the cost of computation forming perhaps wasn't so much an issue.
Yeah, they wouldn't have been that large, I guess.
It's an n-cubed algorithm you're using. It's an n-cubed algorithm to form the matrix. Right. Now with communication costs and so on, it's a rather different picture that we have. So that's probably going back to Limpac, actually, now I think about it. But the properties of these matrices certainly are, well, they're quite broadly available in the stats literature, going back to, you know, textbooks of the 1970s, for example.
Mm-hmm. Interesting. And is your new generator a part of you know, test suites that everybody is going to use now, or what's the state of it in terms of software that's?
Well, I hope so. I mean, we've made it available. So the if I just go back to the link to the paper with Max.
Okay. Yep. Mm-hmm.
We have yeah, there's a link here to the paper. There's a GitHub repository, I think, with the codes in. So you're welcome to try them out. Great,
great. As you say, with the QDWH stuff, we you know, and perhaps you know, doing that suboptimally. So
Yeah, indeed. Actually, to test out our implementation, we use the testing generator from Scalapack, right? So the one that is expensive, the inefficient one.
Yeah.
And indeed, we could definitely accelerate and save some core hours on Shaheen and other system to spend it instead where we should spend it. I have the question on your slide 8, I believe. So, you mentioned that you have little communication involved because you are able to generate on element basis your matrix, of your Q matrix. So, I want to understand why you said little communication. Again, versus no communication at all. If you have a formulation to generate the matrix from an element.
Right. Well, yeah, the communication is when we, so we have to, Q is essentially communication free, but we have to multiply it into the W transpose.
Oh, I see. Yeah.
And that's, essentially a rank 1 perturbation of the identity.
Okay.
And that still requires some communication, but not very much if done carefully.
Got it.
That's basically the answer.
That explains also then why for some of the variant of your algorithm, you're not close to, I guess, linear, ideal speedup.
Yes. Yes, and there's various variants in the paper. Sometimes we have the Q on the left or the right, and so there's different ways of implementing it that have different properties that we do analyze in the paper.
Okay. My second question is slide 18 for the iterative refinement. So you have an OR in your algorithm.
Oops.
I think slide 18.
Oh, this one.
Oh, okay. Oh, 21. Okay. That's right. Yeah. So do you have a secret recipe here? I mean, which one should we go for? You mentioned that GMRS could be a nice alternative, even with a poor preconditioner, LU here. So when one would use the traditional, residual, solving against this residual and the one using with GMRS, for instance, is there a...
Okay. Yeah, I didn't want to go into too much detail here, but I would always use the GMRes version personally.
Okay.
And the reason is that the conditions that guarantee convergence are much more strict for the just plain LU than for the GMRes approach. So we have results that say if the condition number is less than some quantity, then we expect convergence, and the bound on the condition number is much smaller for GMRes than it is for the unpreconditioned problem here.
Is this also the paper with Erin? Is this part of the...
Yes, that's basically from...
Erin and yourself?
Yeah.
Okay, got it. Okay, excellent. Interesting, okay. Interesting. Thank you. All right, do we have any other question from the audience? So we have been recording the session. We'll put, and we have the slides also available on the URL that Nick shared with us. We'll upload the video on YouTube at the end of by today, hopefully. So thanks again, Professor Higham, for your mass guest speaker today.
Thank you.
It was a real pleasure. We learned quite a lot here, and I can see a lot of changes happening in the short term in Scalapack and LAPACK. That's for sure. And of course, incidentally, in our own QWHSVD software. Yeah. It was a real pleasure. All right. Let's thank again the speaker, virtually, I guess.
Thank you.
Thanks.
Appreciate it. Thank you.
Stop sharing. Stop share. Right. Well, goodbye then. I'll head off then. Thank you very much.
Until we can meet physically. We should have been in Manchester today together.
Yeah, I know.
Several of us.
Yeah.
Celebrating Jack's 70th, which was yesterday. So we got him a couple of weeks ago. We got you today. So we're trying virtually to make up for our limitations. And thanks for helping.
Yeah, thanks very much.
Until we get to Manchester a year from now, but see you hopefully well before then.
Yeah. Okay. Bye, everyone. Bye-bye.
Bye.